Hi everyone, this is for our supplementary worksheet for H2 Math in Chapter 9 Functions, right? And in this particular video, we are going to look into concept number 7, which is to determine if a composite function exists, and at the same time, we want to explore how do we get the expression of a composite function. Okay, so a very quick concept is what is a composite function? A composite function is when you pass through an input through two different functions, and the combination of these two functions is what we call a composite function. Okay, so for instance, let's say if we have a composite function gf, right? So the notation gf, right, tells us that we are substituting fx, right? We are substituting fx into the function of g. So means this tells us that x, right, will pass through the function f first, and this whole value of fx will need to pass through the function of g. So for instance, if you notice over here, we start with x over here, pass through the function of f to get the image fx, or to get the object and image, right? Image fx, right? And then it will pass through this g over here to get what we call the gf of x. Okay, gfx. Okay, now so let's take a look at what is the condition, right, so that the composite function exists. Okay, so if you observe in this little corner up here, all right, so once again we put x through the function machine of f, right? And over here we get an output fx over here, right? And for this fx, we will pass through the machine for g, and output would be g of fx. Okay, like that. Or to write in short note without the bracket is just gfx, right? Something like that. Now, so in order for this particular composite function to exist, we need to zoom in to this particular exit over here, right? So we want to make sure that whatever that we output over here, right, right, can fit in the hole for the second function. Okay, whatever that we output over here can fit in the hole for the second function. Okay, so in the set notation, or in the mathematical notation, this tells us that the range of f, which is the set of values of the output from function f, must be a subset, or at least equal to the domain of g. Okay, otherwise it will be something like this. Okay, if you notice at this upper corner over here, so for this case, right, if you notice, the range of f is bigger than the domain of g. So for some of the objects over here, for some of the inputs over here, right, namely these few inputs over here, right, they do not have an image, and this will fail as a function, because the function, right, every object must have an image. Okay, so for this condition over here, the f, range of f, must be smaller than the domain of g. Okay, and how do we determine this? Because this over here is a set, the domain is also a set, so we are going to write this in set notation, or we're going to use interval notation to help with our thinking process. Okay, so this one would fail. Okay, once again, this would fail to be a function, because okay. Okay, so back to this one over here. So the composite function exists only if the range of f is smaller than the domain of g. And let's talk about the domain of the whole process. Okay, so the domain of the whole process would be starting right from here. Whatever you put inside f, the function f, will come out from the composite function gf, right? So technically speaking, the domain of gf is the same as the domain of f, because that will depend on what you put in to the first function. Okay. Now, one more thing that I need to highlight is that you should not be confused with whether the function is a one-to-one function or not. So the one-to-one function is more specifically for inverse function. For composite function, we'll mainly look at the range and the domain, right? Range of the output and the domain of the next input. And we also want to look at the domain of the whole process itself. So for the one-to-one function, please do not bring in to prove that it's a composite function using a one-to-one function, okay? Okay, so now let's take a look at example 6 where we want to determine whether the composite function exists or not, and then we want to find the expression of the resulting composite function. Okay, so we have functions f and g defined like this. So f over here, if you notice, 4x plus 1 over x minus 3. Now, once again, I want you to recognize what form is this. This form is actually our rectangular hyperbola. Okay. Now then for gx, the shape is actually a parabola, okay? And so let's take a look at the domain. X is a real number and x cannot be 3. And for the domain of gx is a real number for all the real numbers, okay? So explain why the composite function fg does not exist. So over here, we need to look at the range of g and the domain of f, right? So you need to look at the range of the first function and the domain of the second function. Okay, so what we're going to do is, in order to get the range of the first function and the domain of second function, we need to look at the graph. Okay, so mainly this is the graph that we are going to look at for fx. Okay, so this is the graph of fx. Now, if you're wondering how do we get this graph, we can do long division and expose the 4 out here. And using the denominator, we have the x minus 3 equals to 0, x equals to 3 as the vertical asymptote. Okay, so this is how we get the graph. And then what do we do next is, let's check out what is the range of g. Okay, so g over here, right, this function g is actually a parabola, x squared, right? So this one, let's take a look at the domain of g. So the domain of g is everything, right? All the real numbers of x. So what is the range of g? Okay, now the range of g, right, what is the minimum value of this parabola? The minimum value is actually 0, 0, correct? The minimum point is at 0, 0. So what we need to do is we need to state the range of g, right, would be minimum 0, so it can equal to 0. So we put a close bracket 0 and infinity with an open bracket over here. Okay, now what is the domain of f? Domain of f would be all the real numbers except for 3 over here. So this notation over here, it means that all the real numbers except for 3. Now let me quickly draw out a number line to show you the size of this range and domain. Okay, so let's take a look at the first one. The range of g, right, is mainly this on this number line over here, and then the domain of f would be this number line over here. Now, as you can see, right, if we want to try to fit this into this set over here, cannot, because there would not be an image for x equals to 3. They cannot take the input at x equals to 3 for function f. Okay, and so because of this, this first set cannot fit into the second set, or this first set is not a subset of the second set. Okay, not a complete subset of the second set. So what we need to write is, now since, right, the range of g, okay, so range subscript g is not a subset of the domain of f, so the function fg does not exist. Okay, the function fg does not exist. Okay, now then conversely, right, on the other side, does it exist or not? Like, does what do you call this? Does the function gf exist or not? Actually, it does. If you just sketch the graph out, you can actually see that the range of f is actually a domain of g. Okay, so because of this, right, they will tell us to find the expression of gfx and state the domain of gf. Okay, so let's proceed on to do the second part. So how do we find the expression of gfx? So gfx over here, right, is just g, and you're subbing the whole of function f into the expression for g. Okay, so 4x plus 1 over x minus 3. So g, right, is actually x squared, correct? So what we are doing is, now the x becomes this whole expression for fx. We are subbing this whole value. square, like that. So this is the expression for g of x. Do we need to expand? I think don't need to expand. We can leave it like this. Now, then what is the domain? Okay, so what is the domain of a GFX? So the domain of GF, right? Concept is equals to the domain of F, and what is the domain of F against all the real number, right? Except for the value of 3, like this. Okay, now also another thing is, let's say if you want to state in a similar form, then we will write over here, so X is a real number and real number like this, and X cannot be equals to 3. Okay, so this is how we write down the domain of GFX. Okay, so let me point you to another side note over here. Just now we mentioned that GFX exists, right? So let us prove why does GFX exist more explicitly. So in order for this function to exist, the range of the first function must fit into the domain of the second function. So let's check what is the range of f. The range of f, right, from this graph over here, right, tells us that the range of f is all the real number except for 4, right? All the real number except for y equals to 4, okay? And then for the domain of G, it is all the real number, right, as defined in the question over here, right? So is this range of f a subset of DG? Yes, it's actually a smaller set. Okay, so because this is a smaller set than the other set, so because of this, the GFX will exist. Okay, so this is something for us to take note lah, if you want to prove that something exists. So the thing, once again, I want to highlight is, does the graph bring marks or not? The graph actually won't bring any marks, but the graphical method is extremely useful for you because it shows you very clearly on what is the domain and what's the range of that certain function. Okay, so I would still encourage you to do a light sketch of the graph somewhere in the working, then you can just state the intervals for your range and domains respectively. Okay, so this is example 6. Okay, so let's take a look at example number 7. And example number 7, same style, we are also finding our composite functions, right? So the function f and g are defined by this f and this g, right? So for fx is ln of this expression, but the domain is restricted to this part over here, right? So the domain of f is restricted to x less than -1. So if we were to write this as an interval notation, so we will start with -infinity and we'll end with -1, and we cannot equal to -1, so we put a round bracket. Okay, then for gx over here, so this one, the domain of g is actually all of the real number. Okay, so explain why the composite function fg does not exist. So let's have a quick sketch first. Which is the first function, which is the second function? So the first function is g, second function is f. Okay, so we want the range of the first function to be within the domain of the second function. Okay, so let's take a look at the two graphs over here. Now the first graph, okay, so this is the graph of y equals fx. You can easily use your graphing calculator to verify that this is the shape. Make sure that you pay attention to the domain and restrict your x minimum, x maximum. Okay, then there's also the graph of gx, and this is an exponential graph, right, and with the horizontal asymptote over here. So something for you to take note. And for the ln graph, one more time, ln graph usually have vertical asymptote at the place where the function is not defined. So exactly at -1, right, there is an asymptote over there. Okay, so this is something for us to take note. Okay, so what are the domains and range? Okay, so over here, let me quickly point out that this is the domain of f, right? Then the range of f would be over here, like this, range of f. Okay, now, and then over here, this is the domain of f, which is the, domain of g, which is the whole set over here, right? And then the range of g is a bit restricted. Okay, so at most, at least -2, and at most infinity, a positive infinity. Okay, so let us write down what is the the range of g and the domain of f. So the range of g, okay, you need to state that this is a minimum -2, cannot equal to -2, and to positive infinity, right? Whereas the domain of f is from negative infinity to negative 1 and cannot equal, right? So both of these sets are, yeah, they cannot fit into each other lah. Okay, if you look at the quick sketch over here, right, you cannot put this first set into the second set. Okay, very, very quick sketch. Okay, and so because of that, so since the range of G cannot be a subset of df, so the function fg cannot exist or does not exist. Okay. Now let's take a look at what they want us to find. Find an expression for gfx and state the domain of gf. Okay, so gfx. So this will be the second part. So means I'm going to sub g and I'm going to sub in the whole function of ln of x squared minus 1 into the expression of g. Okay, so this one would give me e to the power of 2x, right? E to the power of 2, sub in the whole ln of x squared minus 1 like this. Okay, and then outside need to minus 2. Okay, so with this, let us make use of the law of logarithm to put the square up there first. Okay, and then e ln something using your law of logarithm, you will get something like an x squared minus 1 square minus 2. Okay, so this over here is the rule or the expression for our gfx. And what do we need to do is we will need to add in the domain of the gfx. So the domain of gfx is x is a real number, so x is an element of the real number set, right, such that we follow the domain of f, right, so that x is less than negative 1. Okay, so one more time, this thing over here, okay, this thing over here, the concept is the domain of the composite function follows the domain of the first function. Okay. Now, one last thing to take note is over here. Take note of the asymptotes when you're drawing graphs involving exponential and logarithms. So because, right, over here, ln x will have a vertical asymptote at x equals 0. E power x will have a horizontal asymptote at y equals to 0. So you just need to remember that whenever you draw exponential graphs and logarithmic graph, you should have asymptotes, the horizontal and vertical asymptotes respectively. Okay, so something for you to take note. All right, so this one is just an overview of our example 7. And once again, right, I want to tell you that the working not as much. Okay, what you need to do is just get a rough sketch of this graph. Okay, just get a rough sketch of this graph, preferably with the asymptote. And if you want, you can include the axis as well. And then unless they ask that, you just give a rough sketch. Okay, and then what you need to do is explicitly state the range and domain of the graphs, and then to show that fg exists or does not exist. Okay, so this is something for you to take note lah. Okay, so let's proceed on to do it yourself 5. Okay, so you can try to do it yourself or you can just follow this video, up to you. Okay, or if you're lost, then you just come back to this video lah. Okay, so the functions f and g are defined by like this, right? So show that fg exists and state its rule and domain. Okay, so first let's analyze what is this function. We've got the rule. This over here is the domain of f, and then this over here is our domain of g. Okay, and we want to show that fg exists. So this tells us that the first function is g, the second function that will pass through is f. Okay, so something like that. So what we want to do is we want to show that this range of g is a subset of the domain of f. Okay, so this is what we wanted to do. Okay, so how do we find this range and domain? We'll do a quick sketch on one side. So first, we have fx is ln x plus 3, right? So very quickly, you just sketch something like this. Okay, so this is y equals to fx. Okay, so very quickly, let's take a look. What is the asymptote again? So asymptote x equals to negative 3, right? How do you get the asymptote? This one equals to 0, okay? Now, so the range, this is the domain of f, and this would be the range of f. Okay, then let's take a look at the second graph over here. The second graph, right, is a quadratic graph, but take note this is a maximum quadratic graph. So roughly, I'm going to sketch something like this over here. Okay, something like this over here. Now, taking note that this domain of G, right, is restricted, correct? So I don't think I will have all the graphs over here. Okay, so using the GC very quickly, this point is actually 2 and 1, right? It will pass through the origin 0, 0. Okay, and this point over here is a negative 2 and negative 3. Okay, just do a very quick sketch of this, right? And so the parts that I don't really want, right, is actually here, right? So this part, actually, I don't really want this part at the side. Okay, now once more, we will start first with a whole parabola, right? And then we'll look at the restricted domain from negative 2 until 2, right? So over here, let's take a look. This over here is the domain of G, right? From negative 2 to 2, right? And then over here, we get our range of G, okay? So I think it's time to write down our statements already, right? So first one, what is the range of G? So range of G is from negative 3 to 1. And then oh, by the way, this is a hollow circle, okay? Because we cannot equal to this. So this will be a hollow circle. Oops, over here. And this will be a hollow circle over here at the maximum point. Okay, hollow circle. So it will be negative 3 to 1, but we cannot put in this thing over here. Okay, now then the domain of f would be from negative 3 onwards until infinity. So if you were to double check over here, right, the first set can fit within the second set. It's a smaller set than the second set. Okay, so because of this, so since the range of G is a smaller set than the domain of F. Okay, so if you want to put the equal, can, no problem, right? If you want to put a full subset, also can, right? So this one, FG exists. Okay, so this is the first thing. Okay, now second one, state the rule and domain. All right, so the rule is going to be FG of X. Okay, so F of this. So I'm going to put in gx, right? And then pass through the function of f. So it will be ln of whatever that is plus 3, right? So this one will be negative 1 over 4 x squared plus x plus 3. Okay, so with this, this will form our expression for the fgx, and we will state the rule and the domain. So the domain, right, would be following the domain of domain of g. Okay, domain of g, domain of the first function. Okay, so once again, the domain of the combined function, fg, would be following the domain of the first function. Okay, so something for us to take note over here. Okay, so similarly for do-it-yourself 6, we have two functions f and g, right? Domain of f, domain of g. Now determine with a clear reason, right, whether the composite function fg exists. So drawing the whole process out, so we will start with the function g, and then we'll start with the function f. So what we need to check is range of g can fit into the domain of f. So this is what we need to check over here. Okay, so in order to determine the range of G, we just need to focus on the graph of Gx. I actually don't need to plot both the graphs, okay? So looking at Gx, right, we have, once you completed the square, right, we can reveal this minimum point, right, or you can use your GC to quickly find, okay? And the thing is that this Gx, right, has a restricted domain over here. So the domain of G is less than 1. So this tells us that we will probably start from over here, right? And then we'll take the graph on the left. So the graph on the right hand side is the one that we don't really need over here. Okay, so the only part that we need is from here onwards to the left. Okay, so let's take a look at what is the domain of f. So this is the domain of g, right? Then from here onwards right? So this is going to be the range of G, like that. Okay, so using the graph to reveal what is the domain and range lah. Okay, so from this expression or from this graph over here, the range of G starts from -1 equal to -1 up to infinity, positive infinity. Okay, and then the domain of F is whole of the real number. So since range of G is a subset of the domain of F, okay, is a subset of the domain of F, so the composite function Fg exists. Okay, now then how do we find the rule, the domain, and the exact range if it exists? Okay, so we are looking for Fg of x, so it is f of this expression over here, so x squared plus 2x plus 2. Then f, right, is 3 minus 2 of e x plus 1. So sub in the whole expression for x. So replacing this as x, then plus 1. So if you can see what's going on, right, we are here, right, we are replacing the x with this whole expression over here. Okay, right, so this is how we get the fgx. Let's tidy up a bit to something that we like to see. So this would be x squared plus 2x plus 3. Okay, so what is the domain? So the domain of the whole process is starting from the domain of G. And what's the domain of G? Over here. So domain of G is x is a real number such that x is less than or equal to 1. Okay, so this one over here, one more time, the domain of the composite function is the domain of the first function. Okay, then the next thing to do is we want to find the exact range if it exists. Okay, so using your GC, okay, using your GC, you would have gotten a graph like this, something like this, right? So this point over here, right, we want to state the exact range, right? So exact range means range in exact values. Okay, so the maximum point over here is at -1. So subbing in the -1 into this expression over here, we will actually get 3 minus 2e square. No, 2e squared, correct. Right? So subbing in the -1 to this expression, so 3 minus 2e squared, right, would be this value over here. Okay, now then let's take a look at the domain of this whole thing. It is less than 1. Okay, so if you were to zoom in and out of the function, you will find that 1 is somewhere around here. All right, and then we will not be taking this part of the graph. We only take this part to the left. Okay, so so this is what we call graphing the composite function lah, putting the whole composite function in together. So over here, what is the range of G? So dot dot dot, the range of G would be starting from -infinity until the maximum value of 3 minus 2 e squared. Okay, can equal or not? Can equal, so need to put the close bracket, this. Okay, so this one is just to map out what is the or not say map out, to like to look at the graph of the whole of fg. Sorry, this is fg, not r of g. Okay, range of fg. Yeah, so it's to look at the whole graph of the range of fg, whole graph of fg, and look at the range, right? The y possible y values for this. Okay. Okay, so that's all for this video. All right, so in this video, what we covered again is we are looking for the range of composite functions. Sorry, we are looking for the existence of the composite function, and we explored what is the condition for the composite function to exist. And at the same time, also we find the domain of the composite function and to write the rule, the expression of the composite function. Okay, this one over here, the range of the composite function, right, we'll cover a bit more extensively in the next video. Okay, so that's all for this one, and I hope you have a good learning. See you in the next video.